Right, maybe we should started. So today we have JongYeon. It's a great pleasure to have him here on campus. So JongYeon is actually one of the leading junior theorists with lots of expertise in a wide variety of interdisciplinary areas, spanning from atmospheric theory to kind of anybody physics or quantum information, which he will be talking about. So as you might know, he just started his research group at Illinois. But prior to Illinois, he was an undergraduate at Tech, working in Johnson Steel at OSA, and then he moved to Harvard to doing his PhD in Artemis Group. And then he moved to KICT as a fellow, and there he worked with many faculty there for his quantum science. And then he just started his group, and he was talking about one of the side topics. Okay, let's welcome him, and then we'll go through.
Right. Thanks a lot, Juni, for a nice introduction. So today I'm going to talk about many-body physics of information. So first of all, to talk about information, we should it's good to talk about something beyond unitary open quantum system, because if you think about like a unitary transformation, it's really just change of basis. So it cannot really inject or remove information to the system. So, but if you couple your system to environment and if you focus on the system, then information can be manipulated. Then it kind of makes sense to think about like information theoretic property of a given system. So there are like two types of coupling to environment. The first one is a measurement, where your system is coupled to environment, and environment made some observation, and your system gonna collapse in a way consistent with the measurement output. The second type of coupling is a decoherence, where basically the observer measures something of your system, but that outcome is not known to the system, which means that now your initial, if you had a like pure state wave function, it kind of becomes a mixed state. So, for example, let's say your environment is applying some decoherence to the system, like potentially measuring some like operators or something. Then even if you start from the like initial pure state, it's going to evolve into an ensemble of pure state, each of which appears with different probabilities. And basically it means that instead of maybe a familiar wave function formalism, you should talk about some density matrix. So this is a density matrix for a pure state, and under this like quantum channel, your state evolves into an ensemble of states, each of which appear in the probability pi. And you can think of this like psi I as the state psi 0 applied by some kind of operator ki, which you call like cross operator. So this is called a like cross representation of a quantum channel. Question?
What is that lightning symbol?
Which symbol?
Lightning.
Here, I'm trying to represent the decoherence. Some like spark, noise. Yeah. Okay, so what's new in this mixed state formalism? So if you think about your wave function, let's say wave function is a symmetry. Then if you write that pure state in terms of density matrix formalism, you have a wave function level symmetry, meaning that your density matrix will be invariant under left action or right action of a symmetry. That's also called a like strong symmetry. But another like type of like a symmetry is an ensemble level symmetry, where your density matrix is only invariant under conjugation by the symmetry. So from the like maybe a more from different like formulation, if you have a density matrix, it's like you have a 2 to the n by 2 to the n matrix, but you can try to just vectorize it into 4 to the n by 1 vector living in the double Weber space. So mathematically, it's like applying this identity tensor rho into this maximally entangled state. Then in this way, you can think about density matrix as some pure state living in the double Weber space, and there's some kind of decoherence that's like a coupling between two layers. So this is not like the most rigorous way to define mixed state physics, but that gives some intuitive picture which you can borrow from our familiar understanding about pure ground state physics. And in this formalism, you can see that if you have this wave function level symmetry, it's like you have a double symmetry, because you can act in symmetry on the left copy or right copy to still get back to yourself. but if you don't have a wave function level symmetry, but only an ensemble level symmetry, you have to apply simultaneously to get back to itself. So it's like a diagonal part of the symmetry. So yeah, when I was writing a paper, I didn't know about that this notion of strong and weak symmetry was discovered like basically a decade ago. So I know this double to diagonal symmetry, but you can just replace all that with a strong to weak. It's basically the same thing. So in this study of like many-body physics and information, instead of like looking for some conventional observables like conductivity, magnetization, I'm more interested in some information-theoretic kind of diagnosis, like whether system has thermalized or is there remaining resource entanglement or hidden correlation or some quantum memory. And you can ask whether there's any unifying principle to talk about all this information-theoretic basis. So spontaneous symmetry breaking has been a very powerful concept to basically classify a phase of matter at the zeroth order. So like we have like all different families of spontaneous symmetry breaking that allows us to classify different phase of matter. And basically the question is whether we can use this idea to understand open quantum dynamics. So let me give you an example of the system where you only have an ensemble level symmetry, not the wave function level symmetry. So consider a classical eigenmodel. Here, the Z is a Pauli Z operator. You can simply write down your Hamiltonian in this form. And if you think about the thermal state, in the spin basis, which breaks the okay. So your Hamiltonian has an eigensymmetry, which can be written as a product of Pauli X operator. You consider your Hamiltonian commutes with the symmetry action. But if you look at this density matrix, there's a Boltzmann distribution where thermal state is diagonal in the symmetry breaking Z basis. And what it means that you don't have this wave function level strong symmetry, but you only have an ensemble level weak symmetry, right? So the absence of this off-diagonal term in the symmetry breaking basis can be considered as a loss of quantum coherence with respect to the symmetry charge. So when your system lose the strong symmetry, but only have some weak symmetry, you can think that this is another way to think about like thermalization. Maybe this is more refined version of talking about thermalization or onset of classicality. Any question? Okay, I hope that this example illustrates the key point. So now you can think about like a pure symmetric wave function, and that has a strong symmetry. And if it has some spontaneous symmetry breaking, a true physical spontaneous symmetry breaking, let's think about like two-dimensional transfer field quantumizing model. Then its universality class is that of the 3D classicalizing model. But if this thing got thermalized, so only have a weak symmetry, and it has a genuine, again, spontaneous symmetry breaking, this will be a 2D classicalizing transition, which is universality, the 2D model. That implies that there should be some sort of transition between the strongly symmetric density matrix to the weakly symmetric density matrix. And that's what we call double to diagonal spontaneous symmetry breaking, now rebranded as a strong to weak SSD by a series of people. So the situation I'm thinking about is the following. I have a system Q, and I'm like, if you're familiar with Lindbladian formalism, I'm considering the jump operator that is symmetric. Or if you're familiar with the channel formalism, quantum channel, I'm considering the quantum channel's cross operator commute with the symmetry. In this case, like that K, if that K is a symmetric, every trajectory of the wave function will maintain the symmetry, right? So you're gonna, under this strongly symmetric dynamics, you're gonna have a wave function level symmetry throughout the whole procedure. But what I'm gonna suggest is that there is spontaneous breaking of strong symmetry down to weak symmetry. Another way to think about this is that even if all the interactions are strongly symmetric, you may think that in the most generic situation, after long enough time, system should thermalize. System should lose some quantum coherence with respect to the symmetry charge. And I'm saying that that happens in a universal way. But if it happens in a universal way, what quantities would detect this intrinsic transition of the density matrix? So for that, we should go back to how we detect spontaneous symmetry breaking in our most familiar, conventional wave function situation. So in a usual scenario, we have a Hamiltonian, and we have some symmetry group, and we define some order parameter, which transform non-trivially under symmetry group. And then we apply an infinitesimal symmetry breaking field, H. And basically, to this like a perturbed Hamiltonian, you calculate the expectation value of the order parameter. And then you take a thermodynamic limit, and then you take the field goes to 0. If you take a field goes to 0 limit first, then if it's symmetry breaking operator, expectation value will be 0. But if you take a thermodynamic limit first, then this expectation value may not be 0. And this non-commutativity of the 0 perturbation and infinite system size is what really rigorously defines the spontaneous symmetry breaking. So to illustrate the point, let's think about like the simplest case, one-dimensional transverse field-Ising model. So when J is small, you're in a paramagnetic phase. When J is large, you're in a ferromagnetic phase. But ferromagnetic phase doesn't mean that you have a spontaneous order parameter. If you have taken, I guess, Verica or Tritas class, and I don't know, maybe you probably have learned that this ground state is always a ket state, which is a superposition of actually a spin up and spin down. So if you calculate the order parameter, it's always 0. Only when you like apply a symmetry breaking field slightly, this degeneracy is lifted, and you're going to have a sudden polarization. Put differently, if you apply a symmetry breaking field, your wave function immediately loses half of its components. And that sensitivity of the ground state is what defines a spontaneous symmetry breaking. On the other hand, for example, if you apply a small like a symmetry breaking field to paramagnetic phase, you're going to get non-zero magnetization, but that will be proportional to H. If H is small, then it will be small. But if you apply it to this paramagnetic phase, even if it's a 0 when H is 0, it will immediately jump to a non-zero magnetization. It's a very susceptible to symmetry breaking field. That's what defines a spontaneous symmetry breaking. So now, like based on this like understanding, how can you understand spontaneous symmetry breaking of this wave function level symmetry down to ensemble level symmetry? So I can evolve my system under strongly symmetric dynamics, and if it's a channel, it's a strongly symmetric channel that's a channel strength P, or if it's a Lindbladian, that's like how long we evolve, so Pn or like evolution time T. And then at any point in P, I can perturb my density matrix by an infinitesimally unique channel that explicitly breaks the strong symmetry. So I have a rho prime, which is perturbed from rho. And then I can measure the difference between my original density matrix and slightly perturbed density matrix. And in information science, the difference between states, mixed state, is captured by a relative entropy, this quantity. And then I can calculate the second derivative of epsilon, how sensitive your system is under this symmetry breaking perturbation, and that corresponds to the Fisher information. And if the Fisher information like diverge above certain threshold, that means that although your true state is always strongly symmetric, it's very susceptible toward the like breaking away function level symmetry down to ensemble level symmetry. Basically, this signifies the onset of kind of classic quality, if you think about it.
And just to be clear, you're not thinking of evolving forever with a slightly perturbed channel.
No.
At the end, you do a little perturbation.
Yeah, so it's always like evolve and slightly perturb in a tangential direction and see how sensitive your system is. Yeah. So the singularity in this von Neumann, Fisher information quantity is what defines the transition intrinsic to the density matrix. And yeah, so basically in today's talk, I'm going to provide with 3 case studies. The first one is a Eisen Z2 symmetry. Second one is a fermion parity symmetry. And the third one is a charge-Yeon symmetry. In the first case, you will see that although this is a simple Eisen symmetry, the situation is dual to the false tolerance of the quantum error correction code. Oh, sorry, not false tolerance, the error threshold of the topological code. Second case is fermion parity is then related to some like SYK model. In the third case, you'll see that now this wave function level symmetry or ensemble level symmetry, it looks kind of mathematical ad hoc, right? It doesn't look very physical. But I'm going to show that if the continuous wave function level symmetry is broken down to a ensemble level symmetry, there is some Goldstone mode, and that Goldstone mode is what gives rise to what governs the late time physics of a dynamics, which is a hydrodynamic mode. Any question? Good. So first example is the Eisen case. So I'm considering a decoherent channel where the cross operator is ZZ. So I have a spin for every vertex, and basically a channel. I'm applying this a channel for every bond, where the cross operator is ZZ. And then you can think of this as someone is measuring your edge like a ZZ with probability 2p, and then hide that outcome to the system. So under this operation, clearly that even if you start from the product state or pure state, it will evolve into the mixed state. Let's say my initial state is the product of plus. So I have a plus initialized qubit everywhere. And what it means is that if I measure what like this side in Z basis, it's not going to give any information about the rest of the system, right? So keep in mind that measuring the Z basis is explicit symmetry breaking perturbation, okay? Explicit perturbation that breaks the strong symmetry down to weak symmetry. But now, if like this kind of decoherence is strongly applied, then what you can imagine is that this like thing will kind of percolate, and measuring, revealing information in Z basis for one side can provide the information about the distribution of the remaining density matrix. And when that happens, it means that your density matrix undergoes some intrinsic and structural change.
Sorry, you said, I think with one side can break strong down to weak, but doesn't it break strong down to nothing? If you act with sigma Z alone?
Yeah.
Because it's not strong, that's not strong to weak, right? It's strong to nothing.
No, applying Z is a strong to weak.
Does Z break the symmetry?
Z breaks the symmetry, but like a Z, if you think with Z rho Z, if you have a product of X as a symmetry, you get a minus phase, and minus phase on the right side with pencils, so it's still weakly symmetry. Okay. So in the double space picture, I can think of this density matrix as the ground state of this Hamiltonian. Okay, it's just a simple like paramagnetic Hamiltonian. And now I'm gonna provide you this picture just for intuition, but keep in mind that this is like a Renyi-2 calculation, so it should not be taken as literally, because it's going to overestimate the threshold. So this like error channel can be considered as some non-unitary transformation on this now doubled wave function, and basically this is what it looks like. And now let's say your Hamiltonian has this like a sum of squared form. Then by conjugating A tilde, A as A tilde, which is E inverse, this is going to take your decoherent double state as a ground state. Okay, this is the trick called the Witten conjugation. And now you can see that this like a transform Hamiltonian is nothing but just transfer field on upper and lower layer, this X field, and some like the ZZ four-body interaction between upper and lower layer. And if you have taken some course about superconductivity, when you have a four-body interaction, when that's strong enough, I mean, doesn't have to be really strong in the Fermi case, Fermi liquid case. I mean, it's going to develop some mean field, like ZZ mean field, across like the two layers. And when the mean field is formed, that is going to break the Z2 symmetry for individual layer. It's only going to be symmetric under simultaneous action of the Z2 symmetry. Okay, so that's a rough kind of lattice model picture on how, or explicit picture on how this transition is happening. So for this like model for the conceptual guidance, you can calculate the threshold for the phase transition, and you can see that above certain like threshold, there will be a ZZ mean field that develops, and you can calculate some Renyi-2 version of the Fisher information I presented earlier, And you can see that this exactly behaves like the susceptibility of the model, of the like Ising model, meaning that it can diverge after a certain threshold. So it signifies that beyond this critical point, the system becomes extremely susceptible to symmetry breaking nodes. Any small nodes induces extensive global changes in the density matrix. And what's more fascinating is that this situation is dual to the toric code under decoherence. So Z2 paramagnet is dual to a toric code under Kramers-Bonnier duality, and the ZZ noise becomes a Z noise at each edge. So now, the question you can ask for the toric code is, when I have a toric code, if I apply some error, Z error, that is going to make excitation for the pockets, and by measuring this stabilizer, you can identify where the errors are. But above certain density of errors, even if you can correct all the stabilizers, you may induce some logical errors, right? So people have tried to study what's the a critical density of errors where you can go back to the correct logical sector. And this pioneering work by Praskill and his colleagues have shown that this threshold is 0.11, assuming certain maximum likelihood decoder. But the question one can ask is whether we can capture this threshold without referring to any decoding. Because all this information should be already incorporated inside the density matrix itself. By just investigating the density matrix, you should be able to extract some fundamental bound when we lose the logical information. So one way to think identify the robust diagnosis for this is I'm going to explain now. So let's say we are interested in the robustness of the logical information. So you have some logical qubit encoded into say a toric code, and then now you apply decoherence. If you're trying to, then you may apply some decoding and compare the logical qubit, the fidelity between the input state and the output state. But that is going to be decoder dependent, and also that is going to be maybe a logical state dependent. And in order to study this more systematically, what you can do is to simply bend this line and investigate the entanglement between this reference qubit and the entire system. That entanglement is going to provide an upper bound on whatever information you can retrieve about the initial state in a basis independent way. But then how can you isolate the entanglement between your reference and system, especially when system is under decoherence, when coupled to environment? So there comes the concept of coherent information. So let's say we calculate the entanglement and the entropy of Q. That is going to capture the entanglement between R and Q, as well as Q and environment, right? But if you calculate the entanglement entropy R and Q, that is only going to capture the entanglement between Q and E, because the reference and back is completely decoupled. So by calculating the difference, you're isolating the entanglement between your reference and your system, your toric code, see? And that is the quantity called the coherent information. And if you calculate the coherent information for the toric code under, say, Pauli X and Pauli Z nodes, you can see that coherent information undergoes a phase transition behavior. So if you do this for simply the two raw physical qubit, coherent information just change continuously as a function of noise. But now, if you think about this for very large, almost thermodynamic limit toric code, you can see that the red means there are two logical qubits of entanglement surviving. White means a 0 and blue means negative. And it shows that this exhibit indeed some phase transition-like behavior, right?
Is this coherent information RAINY 2 or this?
No, this is the actual von Neumann.
All right.
Yeah. RAINY 2 version, if you calculate RAINY 2 version, it will kind of overestimate the threshold. So it's actually quite surprising that this information theoretic quantity exhibits phase transition behavior.
Should I interpret the negative value?
Okay, so coherent information when it's negative, so when it's maximally negative, it means that there is no interesting correlation between reference and your system. When it's 0, it means that there still remains some classical information. There may remain quantum information, but it's not clear. At least when it's 0, it means that there remains the classical correlation between reference and system. So you can think this red phase as where you have a quantum information, this white phase as where you have you're guaranteed to have a classical information, and blue phase as a no information. Okay, so the summary of the first part is that even under symmetric decoherence, system thermalizes into kind of like a classical ensemble, and this is basically the phenomenology of strong to weak spontaneous symmetry breaking, and it can be detected by various information theoretic metrics. The first one I suggested is the Fisher information, and there is some coherent information or entanglement negativity study for the quantum code cases. And there is also recently some work about different types of metrics, but I want to say that essentially the Fisher information is, giving the observable, which is most analogous to the conventional notion of spontaneous symmetry breaking. And I think what's interesting is that this spontaneous symmetry breaking is also dual to the decoherence induced transition in the topological code. If you do it for Zn, it means a Zn Tori code. I mean, you can always think in this kind of way. And knowing this, I'd like to study whether fermion parity can be broken from the wave function level down to ensemble level. So it doesn't have to be the SYK model, but I chose the SYK model because it's quite fascinating model. So basically, it's not very complicated. It's just like Hamiltonian with like a 4 Majorana fermion interaction with random J coefficient, but you can. When it's IJKL, where each index runs from 1 to n, the number of Majorana, you can reshape this into an n squared by n squared matrix, and you can perform singular value decomposition, and you're going to have like n squared singular values in general. But now you're restricting singular value into not order n instead of order n squared. So that is now the low rank variance of the SYK model. As you're changing, so if gamma is n, that goes back to the original SYK model. But if gamma is order 1 value, as you can see, it's like some variance of that SYK model. And as you're lowering the gamma, the ground state, zero temperature entropy kind of slowly decreases. But what's quite fascinating about this model is that it has extensive zero temperature entropy S0 times the system size. One way to think about this is that if you think about torical Hamiltonian in the torus, its ground state degeneracy is always 4, no matter how large the system size is. But this SYK model, as the system size gets larger and larger, its ground state and quasi-degeneracy gets exponentially large with the system size. So that the ground state, the zero temperature entropy is extensive. So some people have suggested why don't we use this as a quantum memory? It has a extensive, like as we increase system size, the number of logical space also increase accordingly, and maybe it can be a candidate for a good memory. So of course, it's not really a good memory in the sense that we don't know how to encode our information down to this ground state magnitude, nor the distance is not scaling with the system. It can, but it can be made arbitrarily close to the scaling with n.
Does this number depend on how I take the thermodynamic and low temperature limit?
Yeah, that's a very good question. So I split the word quasi-degeneracy. So your temperature should decay in a 1/n to the certain exponent, but slower than that. So otherwise you're gonna resolve the degeneracy.
Right.
Yeah. But it's very tiny degeneracy. So now question you can ask is whether logical information or information encoded in this ground state manifold is protected against noise. So you can think about the symmetry based on only symmetry of this Hamiltonian is a fermion period, okay? And based on this a previous part of the talk, you can imagine that you can largely divide error to types. The first one is the fermion parity breaking noise, where single Majorana is hopping back and forth between system and bat. And the other one is a parity conserving noise, where pair of Majorana is moving back and forth. Okay, and as a diagnosis here, we can use some coherent information with respect to the logical subspace. One way to look at this is you think about thermal field double, where you have a system and reference whose ground state manifolds are maximally entangled, and then you apply a noise channel, and you're trying to see whether this entanglement kind of survives. Okay, so it's the same setup as the coherent information I discussed in the earlier part. Question? Okay. So in this case, we do some like random approximation, and basically to calculate the entropy of like system and entropy of system and reference combined, we convert that into some like a past integral formulation involving the Schrödinger-Dyson equation. And okay, this is all technical details. If you're curious, you can ask me after the talk. But I just want to mention that it can be systematically done for all the higher Renyi quantities, and you can kind of invert it back to the von Neumann by some analytic continuation. So the result is that under the parity conserving noise, it actually stays robust up to a certain threshold and then starts decreasing. But if it's a parity breaking noise, then current information has no robustness. It just like decreases continuously with the error strength. And one way to think about this, the case for the parity conserving error, is that when you have a kind of weak decoherence, basically the information is protected and it's not leaked toward to the environment. But when the this parity conserving noise is strong enough, then it is going to form some mean field of like Majorana bilinear, and then it becomes like a leakage error where information is just lost. And the situation is very similar to the Z2 case I explained earlier. The upshot of like this kind of picture is related to the traversable wormhole. So the way those Google people and Caltech collaboration thought about the traversable wormhole is maximally entangling the ground state manifold of two SYK models and trying to see whether one can send some signal from one side of the SYK model to the other side of the SYK model. So when there's like extensive entanglement between two systems, it kind of provides a geometric shortcut, a space-time shortcut to transmitting information. But one question you can ask is what happens if the one side of the wormhole gets decohered? By the monogamy of the entanglement, this entanglement will get weakened, and the wormhole, traversal wormhole, may close this shortcut at a certain point. So at least the upper bound on this capacity to transmit a signal from one side to the other is captured by the coherent information. And basically what we're showing is that when one side of the wormhole is decohered, depending on the decoherent side, this capacity will change. Okay. All right, now let me move toward the U1 symmetry, which I personally find the most exciting. So now let's think about some charge transport in the Brownian random circuit, which is basically pioneered by Vedika sitting here. So what people have found is that when you have a Brownian random circuit with charge conservation, it's gonna have also some slow charge relaxation mode, which is related to the diffusion. Then the question I asked was whether we can understand this slow dynamics in some systematic fashion. And there comes this strong to weak spontaneous symmetry breaking picture again. So when broken symmetry is a discrete, something can happen, but maybe not too interesting. I mean, interesting thing happens, but not as interesting as a continuous case. But when the continuous symmetry is broken in this way, you're going to get some ghost mode in this double state structure. And I'm going to show that that's related to the emergent hydrodynamics. So again, you consider the strongly symmetric dynamics, which is basically a time evolution under some Lindbladian, where each jump term LA is commuting with the symmetry operator, with the symmetry transformation. And when you apply the noise channel very strongly, that corresponds to the very long time evolution. And based on the general intuition, we can believe that any generate enough Lindbladian should lead to the loss of quantum coherence with respect to any symmetry charge. So it will always break strong symmetry down to weak symmetry. Not always. There's some mathematical condition that Lindbladian should satisfy. For many family of Lindbladian, this is the case. And now, when this happens, what will be some consequence, right? And that's basically what I studied in this follow-up paper, basically 2 years ago. So what does it mean by a strong-free SSB of the U1 symmetry? Let's say you have a one-dimensional or any dimensional system with total U1 charge conservation. And if you have some wave function, the total, although you have a total charge Q, it's kind of delocalized. For every site, it's unclear whether you have a certain number of charge or not. So if you introduce some local gain or loss term, then to the density matrix, it is going to explicitly break the U1 symmetry, but it's only going to generate some epsilon proportional component to the other part of the density matrix, other charge sector. But now, when the strong-free SSB happens for U1, when your density matrix now kind of maximally dephased, so it has only a diagonal entry within this total charge sector, this a gain or loss, local gain or loss, can immediately induce very large component to the other charge sector. Which means that your system becomes very susceptible to the gain or loss. Another way to think about this is that when you have a lot of off-diagonal terms, they kind of coordinate in such a way that you protect your system against local gain or loss. But if you don't have such an off-diagonal term, no quantumness, then your system becomes very fragile against how can I? No. Aaron Lindenberg, can you?
That's just a random.
Okay. Good. Where was that? So yeah, so pictorially, you can understand the spontaneous symmetry breaking up charge U1 in this way. So after this, your density matrix will, without noise, it will always have a strong symmetry because this is just projector onto the total charge sector Q, but it will become extremely susceptible to the noise. And the consequence is what I'm going to talk now. So here, I'm going to consider some Lindbladian, as I think Vedika considered. So at every two sites, I'm evolving the density matrix with some a Brownian random circuit, which is modeled by e to the IH delta t, where this H is basically some charge conserving Hopkin term plus some interaction times some Brownian random variable. So each site and each time, this random variable is different. So you don't have any translation symmetry. But after averaging this random variable, you're going to recover ensemble level translation symmetry, and you get some Lindbladian. So this, after averaging, you get Lindbladian basically given in this form, and under this, Choi isomorphism or doubling trick, you can represent your density matrix of time t as the initial density matrix where the imaginary Schrödinger evolution is applied, where this HL is just the doubled version of the Lindbladian. It has a nice sum of square form. So now, because I have a kind of weak translation symmetry, I can label the eigenoperator of this Lindbladian using the momentum label, the weak translation charge label, and then its eigenvalue, e to the e is also labeled by this momentum. And now let me assume that this ek has a k to the n form, some dispersion. Then I'm gonna recover this one of the correlation between operator at time 0 and time t to be this form. When it's diffusion, the n should be 2. So if diffusion is really a universal behavior, that means that this Lindbladian must have a quadratic dispersion. Another way to think about this is that when you look at this equation, late time physics is governed by the eigenoperator whose eigenvalue is very small. By the way, this is sum of square, meaning their real part of the eigenvalue is lower bound by 0. If it's strictly 0, that corresponds to the steady state under this evolution. But if it's slightly larger, that's going to be the term that governs the late time physics. And to have some late time, non-trivial late time physics, you should have some gapless mode. And to have a precisely a diffusion behavior, you should have a quadratic dispersion. But now, why do we have a quadratic dispersion? Where is this coming from? And I'm basically saying that that's coming from the Gaussian mode of the strong to weak U1 symmetry breaking. So you have this double symmetry, U1 left and U1 right. And because Lin-Varian, I consider, takes the identity on the total charge sector M as a stationary state, I can see that individual, like a projector into the total charge sector, is the exact ground state. And if you have a local Hilbert space dimension, which is a 2s plus 1, then it means that you have a 2s n plus 1 fold degeneracy for your system, for this Lin-Varian Hamiltonian. And each kind of ground state has a U1 off-diagonal charge of 2n, which means that by forming this linear combination, you're explicitly constructing certain ground states where U1 off-diagonal symmetry is spontaneously broken. So now you're left with U1 diagonal part, the weak part, ensemble level part of the U1 symmetry. And okay, so since this is broken, mathematically for this Lin-Varian, I would expect a Gaussian mode. But why a square? So the one way to obtain the Gaussian mode is using something called a single mode approximation. So if you have a certain state size 0, you apply some density modulation operator, and then you do some variational, estimate, and then you can kind of show that this energy has certain, dependency on K. So if you think about the superfluid helium, where U1 symmetry is spontaneously broken, you can see that the numerator is the K-square dependence, and denominator has a K dependence, so that you get linear Gaussian mode. Naturally, if you think about Gaussian mode, linear mode is the most generic behavior. And the reason why we get K dependence here is that this denominator is actually something called a structural factor. And this superfluid helium has a some spatial dependence for the ground state, such that if you calculate the structural factor, it has some non-trivial K dependence. But now, if you think about our state labeled by total charge M, keep in mind that this is just a vectorized version of the identity in the total charge sector M. And you can immediately imagine that such a state should not have any non-trivial spatial structure. And you can calculate that the structural factor is just some constant, has basically a ignorable dependence on the tensor. Yeah, so this is, yeah. So now, and the denominator has again a K-square dependence. So if you have the U1 charge conservation, that means that this Gaussian mode you construct as a K-square dispersion. But if you happen to have some multiple conservation symmetry, then it's going to get softer and softer. So any interesting prediction? I mean, basically what I did is providing some new perspective on how diffusion behavior arises. But now, if you think about situation with, say, a dipole conservation on top of charge conservation, we know that each charge sector decomposed into smaller Krylov sector, meaning that projector onto a specific Krylov sector is another stationary state. And now, if you're familiar, this Krylov projector has non-trivial spatial structure to be decoupled from other total charge sector, and that implies that structural factor is non-trivial. So if you confine yourself to a specific Krylov sector, then the mode can have a less soft dispersion, meaning that it's going to be diffusive, or it can have a chance to be super diffusive rather than self-diffusive under the multiple conservation symmetry. Because the additional symmetry implies that things should diffuse slower, should be self-diffusive when you have a dipole conservation. But you can find certain Krylov sector where it's actually not the case. So this gives the idea about Krylov resolved hydrodynamics, where which was actually observed in some numerical study before, and we have simulated this for a two-dimensional system and numerically confirmed that such a faster diffusion is indeed the case. So summary is that this charge transport dynamics can be considered as the Gaussian mode coming from the strong to weak SSD, and this provides some unifying description for a multiple conserving system, also long range interacting system, which we can show that this Gaussian mode will have a like a k dispersion or even like k to the 1/2 dispersion, which gives a super diffuse behavior. And there's a constraint, it gives also like some non-trivial dynamics. And actually, for me, it's quite interesting that this gives a recipe to construct a Hamiltonian that always breaks the U1 symmetry, even in one dimension. So if you think about Murphy-Wagner, in one dimension, U1 symmetry cannot be broken. But on the other hand, from the generality of the thermalization behavior, you would also expect that this will always give a Hamiltonian that breaks the U1 symmetry in one dimension. So the way to resolve this is a Gaussian mode being a quadratic dispersion rather than linear dispersion. So that's on one way to circumvent the Murphy-Wagner theorem of Gaussian mode being not linear dispersion, and that's explored in my another recent paper. So long story short, if you ask what happens to quantum many-body state under decoherence, the pure state becomes mixed states, physical observable would naively decay just exponentially with the system size and the strength of the noise. But there exists some information-theoretic quantity you can define that undergoes a phase transition behavior, and that is basically the theme, research theme under this many-body physics of information. And I just want to emphasize that the spontaneous symmetry breaking provides a unifying framework to explain various different information theoretic transitions. And now there is a like elephant in the room, which is a measurement-induced phase transition that I haven't talked about. But for that, you should introduce some concept of higher moments of the density matrix as well as the replica symmetry. And that when replica symmetry is incorporated into this picture, then that can provide the more unifying picture about all those information theoretic phase transition, which is I guess my students are working on this, and hopefully we're gonna write about this soon. So now thankfully I still have 10 more minutes. So okay, up to here, any question?
So the statement that you had about the dispersion, it's basically saying that the purity of this overlap that you're taking in the denominator is the purity of that eigenstate of the Lagrangian, right?
In some sense.
Why is that? Why does that like change the dispersion? I mean, I guess you derived it, but is there a physical picture for what's going on?
Simply that if you think of the numerator is I think that's probably somewhat technical, so we can talk after. But okay. You can just zeroth level explanation is just how mathematics work.
Sure.
Yeah. All right. So I want to talk about more experimental friendly this information theoretic phase transition. So I guess you probably heard about how to converting short range entangled state into a long range entangled state using measurements and local like feedback operation. For example, short range entangled state can be cluster state, graph states, and the right hand side, long range entangled state can be the generalized ket state, pH state, toric code, or even fractions. And basically what it means is a short range entangled state, which actually is a symmetry protected topological phase, is considered as a resource. And upon decoherence, this resource may disappear. I mean, our ability to convert short range entangled state into a long range entangled state may disappear, right? So the question you can ask is when such a capacity, stop being a resource, stop like existing. So one example is a 2D cluster state. You simply have a plus state everywhere, and you apply control Z gates for every like neighboring sites. Then, for example, initially you have an X stabilizer, but that evolves into XZZZZ. Here you have an X stabilizer that evolves into XZZ, as you see from this Hamiltonian. And this Hamiltonian is a symmetry protected topological phase in the sense that if you deform the Hamiltonian by respecting these two global on-site symmetry acting on the red vertex and loop-like symmetry on the white edges, you're preserving some non-trivial property. The one thing is there's a string order parameter, which is a product of X on this white qubit and Z on this two red qubit is going to be 1 for this wave function. Now, What it means is that if you measure all the white ancillas in X spaces, that is going to give some long-range ZZ correlation, right? And on top of that, because you didn't perturb the red side, you're going to have this global on-side symmetry, meaning that you're not only going to have some long-range correlation, but also it's like opposite components, meaning that you're going to have a long-range entangled cat state of some sort. And you can have a like non-trivial like domain mole pattern, but you can figure that out and always convert this back into the sum of all 1 and all 0. Okay. Is this clear? Okay. And now let's say we apply some decoherence on this edge qubit. Another way to think about this is that you measure this white ancilla qubit not in the X spaces, the basis which is consistent with the symmetry, but basis that's inconsistent with the symmetry, maybe slightly rotated basis. Okay. So as I said, being a SPT, symmetry protected topological order is really important feature of this state. So if you violate the symmetry, you may think that, oh, this ability to convert this into a long range entangled state may be gone. And indeed, if you think about this string order parameter under decoherence, you can show that that will now always decay exponentially the length of a string. So now, if you may think that, oh, then if I measure all the white ancilla qubit in X spaces, now things will be exponentially decaying. There's no hope to recover long range entanglement. But actually, that's not true. Basically, I showed that there's like, if I measure, even if there's some wrong basis or decoherence, you can still measure, and through some appropriate decoding scheme, you can always retrieve some cat type long range entanglements. Okay. So, and there's even some threshold where beyond which you cannot recover, but under this, you can always come up with some decoding method to recover the long range entangled state. And there is even a decoding Bayes diagram. If you have a true error rate in x-axis and error rate assumed by the decoder, as long as you're inside is a red base, you can always recover this long range entangled state. Then you can ask, how is it possible? Because seemingly the string order parameter that enables the long range entanglement is exponentially decaying. So basically, after decoherence, what's non-trivial is actually a conditional correlation. So after decoherence, let's say I measure all the edges and condition. Let's think about correlation function condition on the measurement outcome. Okay, and if this conditional correlation is still long range correlated with some arbitrary sign structure that we have to invert, then still there's a hope to retrieve your long range entanglement structure. So, and decoding will be just like finding a spin flip transformation to pencil the sign structure of this conditional correlation given S. So this quantity inside the yellow box is really the upper bound for some utilizable correlation. And what we can show is that it's a string order parameter. The order parameter considered to be a diagnosis for SPT is actually some sign summation of this quantity. So even if this is exponentially decaying, this box, the quantity inside yellow box, can have a still long range correlation. But then how can you capture the transition of this upper bound in a very fundamental sense without thinking about decoder? So again, all those information should be already inside the density matrix because anyway, you're getting cat state by just playing with the density matrix. Okay, so I'm gonna just like study the density matrix to get this quantity. So one way to diagnose the SPT state is by looking at this anomalous boundary here. When you have an SPT state right next to the trivial state, the boundary has some non-trivial, gapless mode or symmetry breaking behavior. So, but instead of like placing your SPT next to trivial state, if you perform some weak rotation, you have this setup. And now, if you measure this like strange correlator, which is correlation function sandwiched by the trivial wave function and the SPT wave function, it's gonna behave in a very non-trivial way. And surprisingly, this is actually the setup very similar to the conditional correlation. Because when you measure conditional correlation, you're measuring the edge of the system in a certain basis, right? It's kind of like projecting the state already into some like a trivial state. Okay. So I can think about type 1 strange correlator, which measures the SPT-ness in the single layer in this double space vector, versus type 2 strange correlator, which measures the SPT-ness of the entire system. And what I find is that this type 1 strange correlator is basically the conditional correlation I mentioned earlier. So if you have an SPT state and measure the edges in the product basis, X basis, then it's kind of like sandwiching that with a trivial product state. And what you can show is that some correlation you can extract by decoding is upper bounded by some weighted average of this type 1 strange correlator. So basically what it means is that any decodable correlation is upper bounded by this marginalized type 1 strange correlator, which measures the SPT-ness of the mixed state. So this finding suggests that some structure of the density matrix, like this type 1 strange correlator, can be used as a defining feature, or maybe it's a way to define SPT in the mixed state setup. So what I found is that this type 1 strange correlator undergo a phase transition, meaning that when this is non-trivial, individual layer in the double structure has a like own SPT order, while like if it's a trivial, that means that two layers are kind of interlocked. Like density matrix often the parts become trivial. But there's a type 2 strange correlator, which measures the non-trivialness in this entire density matrix, which undergo phase transition at a higher threshold. So like below PC, you have some decodable information, which corresponds to emergence, like a strong one-form symmetry. And above, you have a scrambled information, which can be only extracted by exponential resource. And there's now totally trivial state. So for the sake of time, if I give a summary, basically this like a job to convert the short range entangled state into long range entangled state has some threshold for the like the faultiness of the protocol, and this is directly connected to the SPT-ness of the mixed state. And I also in the earlier part I talked about some novel types of spontaneous symmetry breaking from the wave function level symmetry down to ensemble level symmetry, and this makes the I think notion of thermalization maybe more refined. And there's now a way to do some classification of mixed state SPT, and you can also talk about all different types of emergent hydrodynamics as a consequence of this symmetry breaking. So as an outlook, there are so many interesting topics, and now maybe it's your job to fill in this question mark. And yeah, that's it. Thanks a lot.
For the interest of time, maybe we can take out one question, and maybe you can talk to JongYeon because he's here also tomorrow. So maybe one quick question if you want to ask. Right, we take this.
So this last bit about the SPT, it's like, okay, it went a little bit fast moving, but it was unclear to me what the key role of like the decoherence was, because it's also true in like the toric code that makes just like a perturbation to the Hamiltonian. And I try to measure the string operators for like the unperturbed model, but those also decay exponentially.
Yeah.
Right. So like, what was the difference between like just making a Hamiltonian perturbation and making decoherent perturbations?
So yeah, that's what I'm saying. Actually, if you think about toric code and apply not the Hamiltonian perturbation, but decoherence, the string. So if you perturb the toric code Hamiltonian, then at a certain point, the pyramidal law Wilson loop will decay in a pyramidal law to area law, right? That's the point where we lose the topological order. Now, if you think about toric code under decoherence, the Wilson loop operator will always decay in a pyramidal law. Then, like, does it mean that at an entire range of P, we have a same like topological phase? No, as I showed in the other phase diagram, right? And basically what I'm saying is that you should look at some strange correlator or some weird information theoretic observable that's defined in terms of non-linear in the density matrix rather than linear in the density matrix. So I guess the decoherence and the unitary perturbation, I guess, is somewhat different.
All right, so let's thank the speaker then.